Hey, just making a supplemental video for the Think Collab. We're in the middle of talking about numbers. I guess we're going to meet again on Friday. And this is a clarification bit about something I was saying last time. So let's remember the Fibonacci sequence. I'm going to go ahead and index this Fn. F naught we take by convention to be 0. F1 is 1, and so on. We have this relation. We have a recursion that determines the sequence, right? We say that, well, if you take the nth term and you add to that the n minus first term, that should give you the subsequent term, correct? And I'm going to forget this part right away because if you recall, one thing that we were talking about is dropping the restriction on our initial conditions, because we can get anything that satisfies this recursion to limit the same way, in the sense that subsequent terms, the ratios of subsequent two terms in sequence, any pair of subsequent terms will be approach phi. So what I'm going to do with this is something a little bit silly. I'm going to add in a completely trivial relation. And now I'm going to look at this as a system. Well, I get a pair of inputs, Fn minus 1 and Fn, and then I'm getting a pair of outputs, Fn and Fn plus 1. And this is a recursion, but it's a linear system. So now I can actually express this in this form. In fact, because it's a recursion, it doesn't matter that I started at the nth term and I'm moving forward one step. This linear operator will just get applied iteratively. So we would have m plus 1 factors of that to get us this far out in the sequence. Well, that's great. We can worry about powers of that thing, but if you know some linear algebra, to take powers of a matrix or a linear operator of this type, the quickest way is to diagonalize. And this is a full rank operator. This is invertible. So basically what I want is this matrix, let's call it A, is going to be related to a diagonal matrix via some choice of change of coordinates. Of course, we want an orthonormal change of basis for this Q, which means that Q inverse is actually the same thing as Q transpose. I'm not going to worry too much about this change of coordinates, though. We'll find those coordinates naturally. I want to find D, which is our diagonal matrix, and that's going to be the matrix of eigenvalues. for this operator. Okay. So how do we find that? Well, the same way we normally do. We want to make the matrix A minus D. We want to trivialize this. And first of all, we only really need to hit up one of the eigenvalues at a time in order to trivialize, singularize, I should say, not trivialize. It doesn't have to be the zero matrix. We want to singularize this thing, though, which means that we're going to take its determinant and set it to 0. We're solving the characteristic equation, in other words. So what was A again? Here, I'm going to write it all together. So A had a 0 up top, so we got minus lambda, we've got 1, we've got 1, and we've got 1 minus lambda. And so we're going to get and, well, it's a quadratic equation. We can solve this. And you can complete the square, whatever. Maybe you just remember the, well, it's irreducible. You can see that. We're not going to get integer roots. What we do get, if you just remember the quadratic formula, or you can complete the square, solve it however you want, we get a solution that looks like this. And so these are the two roots. I'll just go ahead and separate them out. Lambda 1, we want to be our first root. I will take the positive branch of this guy. And that number happens to be the number we call phi, or the golden ratio. Lambda 2 is going to be the opposite. If I just take the minus here. And here is one place I misspoke on our last discussion. I said that the second eigenvalue was phi inverse. This is actually minus phi inverse. And that's what we want, because if you look back at the original matrix A, the determinant of this guy was minus 1. And so we need the product of the eigenvalues to also be minus 1. Okay, well, that's good. We know our eigenvalues. We haven't determined the change of coordinates, right? And well, let's look at let's see if we can determine what our eigenvectors are going to be. Right, if I want this matrix what's got to be true? Well, the first coordinate of this product is just y. So y needs to be lambda times x. We have a free variable here in the form of x, so I'll take x to be 1. And then we have, again, this isn't normalized, but what we have is a vector of the form 1 lambda. Lambda, which in this case was phi. We want it to be specifically this golden ratio. So that gives us an eigenvector with this first eigenvalue. Now, this eigenvalue is bigger than 1, right? It's positive, and it's larger than 1 in magnitude. Well, you can see root 5 over 2 is going to be a bit over 1. And so this is a bit over 1.5, which is what we want phi to be anyway. This is going to be negative and less than 1 in magnitude. So basically, this eigendirection is going to be expanded out, and this eigendirection is going to be compressed. But as we take larger and larger powers of this linear transformation, we go out n-fold, then we're compounding this, we're getting phi to the n and phi to the minus n. Again, this negative will make it flip-flop direction each time, but let's look at a breakdown of what we have here in the plane. So I've got one eigendirection. I'm going to change colors here for a second. One eigendirection that is going off in this way. And again, what we're going to have here, there's different ways of thinking about it. I like to think of it as the spectral theorem, although we don't need that for finite dimensional operators. What we do get is an orthonormal basis of eigenvectors. So we're going to have a fully orthogonal coordinate system, just a translated coordinate system, in which this direction gets expanded every time, and this orthogonal direction of minus phi inverse gets contracted each time. And so in the limit, as we let n go to infinity, this component gets projected off. The only bit that survives is the part that's going in this direction, the 1 phi vector direction, and that's getting expanded infinitely. And of course, we expect that. The sequence, no matter how we start this sequence, as it follows this recursion, it's going to get arbitrarily large. But the only component that is surviving and becoming arbitrarily large is this specific component. And what is this? This thing, this line, has a slope of exactly phi. And that's where this ratio comes from. So, we start out 0, 1, and then we go to 1, 1, and then we, 1, 2, okay, up here, and 2, 3. So, again, just very slightly above the line here. And you can see they're already approaching that line. They're going to approach this line tighter and tighter and tighter as the sequence goes on. But it really wouldn't matter if we had started with 17 billion, negative pi or something. It would still tend to this same line. And that's what the linear algebra is telling us here. Because that's the nature of this recursive operator that we're applying. Here, I have given you, because it's the solution to a quadratic equation, This is an exact value for phi, not phi to the n, but just phi. And so it is an algebraic number. And this goes back to something Dr. Linney said, not on our last discussion, but on one of our previous talks, the first one I joined in on, I think, talking about phi and pi over 2 being within experimental error of one another. Of course, they're not experimental units. They're exact numbers. And we know pi is not an algebraic number. It's transcendental. But here is an exact, we don't need to perform any experiment. There is no need for an experimental error because this is an exact number. And pi can also be evinced as an exact number. The strange thing is you might think that pi is an experimental number. I mean, the Greeks definitely thought that circles were real and they considered it experimental. They also thought it was exactly 22 over 7. But in fact, there is no perfect circle in physical reality. In fact, there's no avoidance of just the intrinsic curvature of, space-time, right? We don't have Euclidean coordinates except in our minds. And that's why we have to do these idealized, these perfect mind experiments in order to get at these numbers, thus avoiding the experimental error. Anyway, I think this is a kind of a beautiful way of approaching this concept of not only the Fibonacci sequence limiting to phi, but any sequence defined by this recursion, no matter what your starting point is, will satisfy this relation of subsequent coordinates. The ratio between subsequent coordinates limiting to this number phi, regardless of where you started. And that's kind of a high-level approach, but for somebody like me who thinks about Lie groups and dynamical systems and operator algebras, this is kind of a nice, clean way of looking at it. So I hope you enjoyed it. I hope you got something out of it. Thanks.